recording. Something's wrong. Just let me start all over again. Okay. Is it recording? It is, right? Okay, good, good. Okay, let us get started. So we started talking about Feynman diagrams. That's basically sort of the last subject of the course. In some sense, this has been the goal all along to get to in this primer to quantum field theory. So we are dealing with quantum chromodynamic, electrodynamics, where the only new term, in addition to the free theory of photons and free theory of Dirac fermion, is this term. And this breaks down into 8 pieces we talked about. So there is the vector potential field, which has annihilation operator and the creation operator for photons. Here's the Dirac field bar. That's the Hermitian conjugate times gamma naught. That's one of these matrices, which contains the creation operator for the electron and annihilation operator for the positron. And Dirac field here contains annihilation operator for the electron and creation operator for the positron. So within this single term, there are actually 8 combinations of them. And we did look at each one of them. So this is a direction of time so that we follow from right to left as the equations are written. So the one piece is that this psi annihilates an electron that existed in the initial state, creates an electron with the speed dagger to go to the final state. At the same time, it can create a photon using this A dagger operator inside A mu. So that's 1 out of 8 pieces. And if we use the annihilation operator for the photon instead with the same, the rest of the fermion pieces, then you get this diagram. We also talked about positron. So D annihilates the positron in cyan. D dagger creates a positron in magenta. So that's this combination over here. And again, it can absorb or create a photon, depending on whether you pick annihilation operator, creation operator for the photon. And there are also kind of new pieces which didn't exist in non-relativistic theories because matter and antimatter can annihilate. So in this case, I use annihilation operator B for the electron, annihilation operator D for the positron, and then creates a photon with A dagger. That's another piece. But again, I can use the annihilation operator instead. Then you have this funny diagram of electron, positron, and photon all come together and annihilate, disappear from the universe. And there's also the inverse process of all of this. So you can create an electron positron together with a photon, or a photon is annihilated and turned into electron positron pair. So this is a pair creation process. So what we see here is that now that we have antimatter in the relativistic quantum field theory, you have these processes of matter-antimatter annihilation or matter-antimatter creation. So this is a new process we didn't have in non-relativistic theories, but we do have now in relativistic quantum field theory. And that's where we need to have the savior from the complete annihilation, which could be neutrinos, as we talked about, I think, a week ago. So we need something actually to save us from complete annihilation. We don't know what exactly that is yet. That's why people are studying it. So anyway, so that's the immediate consequence of writing down this term, which was forced on us by the gauge invariance of the electromagnetism. Then immediately you led to the conclusion that you have these 8 different interaction processes. And I hope you see that this is really no way out of this, no ambiguity. Once you have this term, you have this collection of 8 interactions. And there's no ambiguity, nothing made up here. Everything is just an immediate consequence of writing every field in terms of creation annihilation operators. So this is a straightforward consequence of this term in the interaction Hamiltonian. So that's what we talked about. Any questions about this?
I have a question.
Go ahead, Chirag.
I've never seen the triple annihilation or the triple creation even as like components of other Feynman diagrams. Can you just say a little bit where they show up?
Yeah. So at least from this expression, all I'm doing is to pick up 3 annihilation operators, right? B for the electron, D for the positron, A for the photon. So I annihilate electron, annihilate positron, and also annihilate the photon. That's why the diagram looks like this. Then you might complain that this can never happen because electron positron at least has the energy of mc squared, and photon also has positive energy. So the initial states has at least 2 mc squared of energy. But if they all disappear, then energy is not conserved. But it turns out that that complaint would apply to all of these 8 interactions because, for example, the free photon can never turn into electron-positron by satisfying energy momentum conservation. Again, electron-positron pair has energy of 2 mec squared, but with no momentum. But if the photon has 2 mc squared of energy, it should have the momentum of 2 mc, but this photon has 0 momentum to conserve the energy momentum here. So none of these processes is actually allowed by energy momentum conservation. But as we learned in the process of the time-dependent perturbation theory, intermediate states do not respect energy momentum conservation, and it's okay because that's allowed within the uncertain principle. So even though none of these, what we call vertices, are allowed from the point of view of energy momentum conservation, if they are used as a part of the intermediate step in the interaction, that's okay. So in that spirit, this triple annihilation process is also allowed. And it can actually lead to for example, Compton scattering. So if you use this one here, imagine this electron is a real electron, this photon is a real electron, but then this positron is a quote unquote virtual positron. Then I glue this diagram together with this one over here, this triple production. Then this is the positron that's virtual. And this vertex creates photon electron. So I went from initial electron photon here to the final electron photon over here by gluing this cyan line for the positron and this magenta line for the positron. So that's actually part of the Compton scattering process. So as long as one of the particles or more are virtual, you can conserve energy momentum from the real initial state to the real final state, but not with the intermediate state. And this triple annihilation process and triple creation process, it turns out to be actually part of your calculation of the Compton scattering. Does that answer your question?
Yeah, thanks.
And sorry, I misspoke your name. Are you Addy?
No worries.
Yeah, sorry about that. That was the bottom of the screen, name was cut off, so I didn't actually get the right name. Sorry about that. Okay, did I answer your question then?
Yeah.
Okay, good. Any other questions here? All right, so at least I hope you see that this is a straightforward consequence of what we have been doing all along, namely to write field operator in terms of creation and annihilation operators. And these 8 possible interactions just immediately follow from this interaction term in the Lagrangian. And then we introduce this convention to draw arrows to follow along the momentum flow. And in the case of antiparticle, we use this funny convention that the arrow is now backwards in time, but this is just a convention. So when you just draw a line, you can't tell if you're talking about electron or positron. By drawing arrows, now you can. So it is just for that purpose. But it turns out that these arrows turned out to be actually useful because when you write down the Feynman amplitude, namely matrix element of some scattering process, then it really looks like you follow these arrows in writing down the amplitude. So you're going to see the explicit example of that. We started looking at the electron-proton scattering, and there you see actually this coming in. Okay, so we started looking at the electron-proton scattering. Now I have the similar terms for both electron field and proton field. Both of them are Dirac fields because they have spin 1/2. Charge is the opposite. So electron has charge -e, proton has charge e. So the relative sign is the opposite between these two terms. But idea is exactly the same. So using this operator involving electron field, I have those 8 vertices. Using this term together with the proton field, I have 8 vertices. And none of these vertices by itself conserve energy momentum conservation. So I need to use at least 2 vertices to come up with a process that conserves energy momentum. And here's one such diagram. So using this proton side of the operator, I annihilate the proton. And inside this proton field, annihilation operator comes together with the positive energy solution U. So when you actually use this annihilation operator, that will leave this positive energy solution as a part of this matrix element. Then I have gamma nu. And then using creation operator proton inside psi bar. So that's the creation of proton now into a different momentum after scattering process. Then inside this psi bar, that creation operator comes together with the complex conjugate of the positive energy solution, U bar PF. So the matrix element in the end, from the proton side, looks like this U bar PF, gamma nu, UPI. That's where these arrows actually make sense. Namely that when proton comes in, that comes with basically this initial wave function, positive energy solution Dirac equation, and put gamma nu there where this interaction happens, and U bar PF for the final state. So that's how this arrow actually makes sense. So as a result, and the final amplitude really does contain this U bar PF gamma nu UPI piece in it. And you do the same thing for the electron. So when you actually use this annihilation operator for the electron, you pick this UPI solution, which is supposed to come over here, it's over here. And then it's UPI, and there's a gamma mu. And then psi bar E picks up again the other solution, U bar PF. So this piece turns into U bar PF gamma mu UPF PI. So that's the electron side of things. And then this A mu actually propagates from one point of interaction to another point of interaction. And we learned that we need to time order them, namely that there are two ways of time ordering them, whether electron emits the photon first, and that would be absorbed by the proton, or proton emits the photon first, and that gets absorbed by the electron. So these are the two possible time orderings. But whenever you have this kind of internal line in the process, then you are supposed to sum up two possible time orderings anyway. So it's convenient to do the sum before doing any computation. And that sum is what is called the propagator. So when you use the propagator, which comes in the form of minus IG mu over Q squared, where Q mu is the full momentum carried by this virtual photon, then this propagator is already a sum of two time orderings. So you don't need to compute two diagrams separately, but instead you sum them up into a single diagram by replacing these yellow lines by this propagator. So once you know the rule, at the end of the day, writing down the matrix element is very simple. So on the proton side, you have this initial wave function U capital PI, and that interacts with a photon that comes from this factor of I over H bar times CE and gamma nu. So that's the factor over here. And here I really took this natural unit. So I actually dropped C and H bar from the expression, assuming that I'm in the unit system where C is 1, H bar is 1. So that's this vertex over here. And then final state, quote unquote, wave function for the proton, U bar capital PF, just by following these arrows. Then I do the same thing from the electron side, U of PI interacts with this minus I gamma mu and goes to U of PF for the final state. And that's this side of the line, again, following the arrows. And between these two vertices, I need to stick in this propagator of the photon. So once you see this expression, now you can see that the Feynman diagram is very powerful. Namely that once you draw the diagram, every piece of the diagram actually corresponds to one mathematical factor inside this matrix element. Line corresponds to this wave function. Vertex corresponds to this gamma matrix. The final line corresponds to, again, the wave function. This wavy line corresponds to the propagator, and so on and so forth. The minute you write down and you draw a Feynman diagram, then you know immediately what the amplitude actually looks like. So we don't need to go back to this time-dependent perturbation theory, think about creation annihilation operator, and so on and so forth. The minute you have the diagram, immediately you write down these expression for the matrix elements, and that's really the beauty of the Feynman diagram. So I hope you see by inspection that what we have done with the time-dependent perturbation theory immediately translates to this diagram and this amplitude. And once you actually get sort of used to it, you can do this almost unconsciously. When you think of the electron-proton scattering, you exchange a virtual photon, so you can think of this diagram pretty much right away. And once you have this diagram, it's not just a picture, it means a lot, because that precisely corresponds to this amplitude or matrix element of this process. And once you have the amplitude, then of course, Apr square of that amplitude gives you probability, and you go back to Fermi's golden rule, and that ends up giving you the cross-section for the scattering process. And we will see how that actually works in a moment. But anyway, so getting this amplitude from this time-dependent perturbation theory, this way becomes very intuitive and in some sense automatic. So that's the point I want to get across on this slide. Any questions about this? It's a kind of important point, right? Obviously. No question? That's kind of surprising. Sure.
Well, I did have one question about the propagator.
Hmm?
So it essentially what we're doing is we're summing like two different paths for like this this photon, right? So like it's a consequence of like the path integral formulation, correct?
Well, so in the spirit of what we are doing, it is just that we have this creation-annihilation operator inside this photon field, and you just sum two pieces where this A nu is creation operator, this A mu contains annihilation operator, that's one piece, where A nu creates a photon, so that is actually this diagram. Or if you pick annihilation operator here, sorry, the creation operator here, and annihilation operator there, that is this diagram. So from the point of view of just the algebra, I'm just picking which one corresponds to annihilation operator, which one corresponds to the creation operator. So once you have this expression, I automatically get those two pieces. So I don't need to switch to a different language of talking about path integral quantum mechanics or anything, just automatically that arises as a part of this matrix element. And of course, you can add this intuitive understanding based on the path integral language of the quantum mechanics as well. But that's actually a fairly complicated thing, because then you have to define what you mean by path integral for relativistic particles. That's not what you see in quantum mechanics textbook. There is actually a way of doing it. So maybe I post a lecture note on that one. Maybe it's already on V courses, actually I haven't checked. So there's a way of doing it, but it's actually not that convenient language. So as far as we are concerned, we are just working out the piece coming from creation here, annihilation there, versus creation here, annihilation there, and sum them up. And that gives you this propagator. And that's something I show it again on our next slide, using Klein-Gordon field as an example. Again, so there's no ambiguity. Nothing is sort of made up on the way. It just follows one step after another to arrive at this expression for the propagator. Okay, any other questions?
Oh, there's a question in the chat.
Oh, okay. Are we just ignoring the zero in first order terms in the Taylor series expansion? Ignoring zero. What zero are you talking about, Chirag? I'm sorry. Or maybe what you're talking about is, okay, so from this expression of the exponential of the interaction Hamiltonian to the next line with this interaction Hamiltonian inserted in this the matrix element, you're completely right. It starts with 1. So you have to compute a matrix element of 1. But if you're talking about electron and proton in the final state to have different momenta from electron and proton in the initial state, and then matrix element of 1 is identically 0, because electron with one momentum and electron state with another momentum are orthogonal to each other by the delta function normalization. So that piece 1 drops out from this matrix element. So that's the first piece. When you go to first order expansion, I have either this operator or that operator, but not both. And this operator can change the electron initial momentum to final momentum. But then either you create a photon or annihilate a photon, which doesn't exist either in initial or final states. So first order term in interaction does not contribute to this process of EP going to EP. So that also drops out. In second order in interaction, you can use this operator twice without using the operator for the proton. But then electron has to be annihilated twice, but you have only one electron initial state, so that doesn't contribute either. So up to the second order in perturbation theory, every other pieces coming from the Taylor expansion of this e to the SI drops out from this matrix element. And this is the only piece that contributes at the end of the day. And I also forgot to mention that second order perturbation, of course, comes with 1/2 factorial. But this is the cross term coming from this whole thing squared. Cross term comes with factor of 2. So that cancels 1/2 factorial from the Taylor expansion of the exponential. That's why I don't have factor of 2 or 1/2 here. So they actually canceled out. And that's how I'll arrive at this piece as the leading contribution to the scattering process. Does that answer the question, Chirag? Okay, good, you got it. Excellent. Any other questions? And these are all important questions, so I'm glad that you're asking these questions. Everything makes sense? Okay, so now that you're looking at the homework problem, which is actually in a very convenient limit where things become very simple. So we're looking at the limit where proton is infinitely heavy. And that's not a bad approximation because the proton mass is 2,000 times heavier than the electron mass. So in that limit, by using the positive energy solution, you are showing that only the zero piece in here is non-vanishing. Other pieces are suppressed by the velocity of the proton. So this new index is uniquely zero. And because this is G mu nu is a diagonal matrix, +1 - 1 - 1 - 1, if nu is 0, mu must be also 0. That tells you that I only need to compute only one matrix between the initial and the final state, the positive energy solutions for the electron. So you only need to do 4x4 matrix multiplication once for a given helicity combination of the electron. Then I'm asking you to compute that 4 times with the helicity positive and negative for the initial state, helicity positive or negative for the final state. So you compute 4 different matrix elements. So that's what you are doing right now. And what you will find is that when the electron scatters backwards, comes in this way, and exactly goes backwards in the opposite direction, then angular momentum conservation along the motion of the electron forbids the helicity to go back to the original one, because the angular momentum gets flipped and it's no longer conserved. So you are supposed to observe that this matrix element vanishes for that case. But at the same time, when you take the massless limit, no matter which direction it goes, you also find the helicity is always conserved, because in that limit of massless fermion, as we talked about, I think last week, Dirac field would split up into 2 biofermions, and each biofermion has a Higgs helicity. So in the massless limit, then helicity always conserved along these lines of the arrows. So that's another thing you are supposed to observe. So this is the way you can make sense out of the matrix elements you work out. So matrix element looks like just an algebra, and you get some answer, and it doesn't give you much intuition on the way of calculation. But once you stay at the final result, it starts to make sense by considering these various limits, where what is conserved, what is not conserved, and so on and so forth. So, these expressions in the end can make an intuitive sense to you. And that's the exercise I want you to go through. So algebra is just algebra, but at the end of the day, you need to stop and admire the result you got, because they start to make sense from the intuitive point of view. And then you appreciate that what you have done actually makes sense. So that's the exercise I hope you would go through by doing the homework problem. So any questions on that? No? Okay, so if you have any questions, you can always come back and ask. Okay, and I forgot to mention this energy momentum conservation factor, which simply comes from the fact that each creation annihilation operator comes with e to the IPX kind of factor. And I'm supposed to do x and y integrals. So y integral will produce a four-dimensional delta function that pi minus pf equals q from this vertex. And second, for spatial integral of x integral enforces the q is the same as capital Pi minus capital PF. Then if you integrate over q for momentum, that would reduce to this four-dimensional delta function that enforces the full energy momentum conservation from the initial state to final state. So once you go through this virtual state that doesn't conserve energy momentum, the final amplitude does conserve energy and momentum. And that's what's allowed by the uncertainty principle in quantum physics. So at the end of the day, everything does conserve energy and momentum. So that's another thing I was supposed to mention and I forgot just a moment ago. Any question about that one? Okay, and as I also mentioned, when you do the y integral, that gives a delta function of electron momentum minus electron momentum equals full momentum of this photon. So energy momentum is formally conserved at this vertex because this photon for momentum is the initial electron momentum minus final electron momentum. But that photon momentum, in some sense, violates energy momentum conservation because q squared, energy of the photon squared minus momentum of the photon squared is not zero. So it does not satisfy the usual relationship between the energy of the photon and the momentum of the photon. And that's why this violates energy and momentum. So this cannot be a real photon. We call that a virtual photon because of that. So each vertex formally conserves energy momentum so that you know what q mu is for momentum carried by the photon, virtual photon, by looking at the initial photon electron momentum and the final electron momentum. So this q is really pi minus pf. But the fact that q squared is not zero means this is the virtual photon. And if q squared was zero, of course, this propagator doesn't make sense. It diverges. But because photon is virtual, this does make sense. It's not infinite, it's finite, and becomes part of this Feynman diagram, and therefore becomes part of the matrix element. And it turns out that this one over q square factor is what it means to have the Coulomb interaction between the electron and proton. So if you work out the energy momentum conservation in this process, it's a scattering process. So initial electron energy and final electron energy are the same. So what that means is that this q for momentum doesn't have the time component, has component only in the spatial component. So this q squared is actually negative q vector squared in the momentum space. But if you remember, negative q vector squared inverse is how you work out the Coulomb potential by solving Poisson equation. Poisson equation is Laplacian is delta function. And if you go to momentum space, Laplacian is q vector squared. Delta function is 1. So the solution to Poisson equation becomes 1 over q squared. And the Fourier transform of that turned out to be the Coulomb potential 1 over 4 pi r. So it turns out that this exchange of the virtual photon is the Coulomb interaction in the language of the quantum field theory. And this also makes sense because when you're talking about quantum field theory, now you start with a field, but everything becomes particles after quantizing them. The even Coulomb potential is supposed to be created by sending particles back and forth in some way. Then it turns out that some of these two different time orderings of sending photon from electron to proton or proton to electron, some quantum mechanically in the amplitude level, is what the Coulomb potential is. So here we are learning something new conceptually, namely that any interactions in quantum field theory are supposed to be generated by sending particles sending virtual photon is the Coulomb potential. And that's the new conceptual understanding. So Coulomb potential in the classical mechanics or even quantum mechanics was an instantaneous potential. And things move inside this potential. But potential, after all, is created by a static electric charge you are interested in, like a hydrogen atom where electron is moving around in a Coulomb potential created for the proton. What you're seeing here is you have this infinite heavy proton, and that proton creates this virtual photon, and that virtual photon gets propagated to the electron, and the electron feels that virtual photon, and that is the origin of the Coulomb potential. That's the way we understand what Coulomb potential is in the quantum field theory language. So all these interactions and potentials we talked about in quantum mechanics are supposed to be due to an exchange of a virtual particle. So that's the new conceptual advance by using quantum field theory. And this is the first time you are seeing that phenomenon. So I hope that makes sense. And again, I believe there are some questions about the concept too.
I have a question.
Go ahead, Cameron.
Is it possible for, I guess, in this, like, of all the possible, some over history, is that like the virtual photon will actually make the like electron and proton, I'm sorry, like electron scattering, like can they actually make them attractive?
Okay, so at this lowest order perturbation theory, it turns out that the sign of charge doesn't give you any difference because you take the absolute square of this anyway. And that's also true in the usual calculation of the Rutherford scattering. The scattering cross-section is proportional to charge squared of the projectile and charge squared of the target. So the cross-section doesn't depend on whether the force is attractive or repulsive. And in the case of Rutherford scattering, that's all you get. So you are led to the conclusion that the sign of charge never matters. But in quantum theory, you can go to higher order diagram where you have electron coming in, exchange a photon, but the next electron also exchange virtual photon to the proton. And then you get a diagram that looks like a box. On the top side, electron comes in, emit a photon, goes horizontally, emit another photon to go to the final state. At the bottom of the diagram, proton comes in, absorbs a photon, goes horizontally, absorbs another photon, goes to the final state. So you have that kind of box-like diagram. In that diagram, I use electron charge twice, proton charge twice, and I'm supposed to add this new diagram to this lowest order diagram. So the relative sign between this lowest order diagram and box diagram actually knows the sign of charges. Then in QFT, the sign of charge does make a difference. And that leads to the idea that proton and electron can bind because their charges are opposite, but electron and antiproton would not bind because their charges are the same. So QFT knows better than the classical mechanics or quantum mechanics by looking at the scattering process. Lowest order is what reduces to the Rutherford scattering cross-section. It turns out that's exactly the same in the non-relativistic limit. And that's sort of in some sense reassuring that what we are doing with QFT actually makes sense. It reproduces known physics, which after all agreed with the data of the Rutherford experiment. But it can go beyond that. And if you go to higher order perturbation theory, then you find the next diagram that can tell whether the interaction is repulsive or attractive, which of course we know. Electron and proton do bind, electron and antiproton don't. So QFT knows better than the classical mechanics or quantum mechanics, knows better about the nature of the electromagnetic interaction. It can tell whether the force is attractive or repulsive, but not at the lowest order perturbation theory, in a way consistent with what we know from the Rutherford scattering. So that's the way we can actually tell the difference between attractive and the repulsive potential. And if you also think of the electron wave function in the Coulomb interaction, you might remember that it's actually e to the minus r over Bohr radius, right? And if you write this in terms of the fine structure constant, it goes like e to the minus fine structure constant times distance over m, a mass of the electron with C and H bar. So if you do a Taylor series expansion of the electron wave function, leading order piece is alpha, namely charge of electron squared. So that part doesn't know the sign of the charge. But the second order piece is alpha squared, which contains both electron and proton charge in it. So the relative sign between the first order piece and second order piece really does know the sign of the charge. That's why you get a wave function that damps exponentially. If you have the same charge, the corresponding wave function would look like e to the plus r. And that doesn't give you a normalizable state and hence no bound state. So that's the way electron wave function knows about the relative sign of the charge too. So if you're looking at only the first order piece, you don't know. But if you look at the relative sign between pieces at different orders in the expansion in alpha, you do know that it's a bound state instead of a continuum state. So it's the same idea here. Only when you consider interference between diagrams at different orders in perturbation theory, you can tell the relative sign between two charges, and hence that gives you an idea whether force is attractive or repulsive. So that's something you knew all along in the hydrogen atom wave function. Probably you haven't heard this story before, but it's true, right? So the hydrogen wave function is a bound state, but only because the exponent has a product of electron charge and proton charge, which is negative. That's why you get this exponentially damping bound state wave function. But if you go to the opposite charge, it grows exponentially, it doesn't bind. So only the relative sign among different orders, right, in Taylor series expansion is what knows about the relative sign of the charges. Does that make sense?
Yeah, definitely. I think the thing that I was seeing was that I was watching this one video about it's kind of like an educational explanation of QFT, and I think they were trying to go over the idea of the path integral for this interaction. And so they're there's a non-zero probability of two electrons actually interacting via a virtual photon and actually attracting each other. And I didn't necessarily know if that was right or wrong. And so
yeah, I don't know if that explanation makes sense. Yeah, you should point me to that video. I try to watch it and see if I agree with that explanation. So can you do that?
Definitely. Yeah.
Okay.
All you want.
Good. Any other questions? So anyway, so just by writing down this diagram, you can immediately write down this matrix element. As I said, that's the beauty of the Feynman diagram. But in it, there is this conceptual development going on that the forces are due to the exchange of virtual particles. So that's a new concept we arrived at by looking at this very simple example of the electron-proton scattering that reproduces the Rutherford scattering in a non-relativistic limit. But it has this idea that it knows the relative sign between the attractive and repulsive forces once you go to higher orders in perturbation theory. So QFT knows more than what the standard classical and quantum mechanics do. Okay, so this was a derivation I showed how propagator comes about. So this is the answer to Miguel's question just a minute ago. So from the QFT point of view, all you do is to pick up creation operator from one field operator and annihilation operator from the other field operator. And here I specifically chose complex triangular field to tell you an idea that this has to do with also matter and antimatter. So if I pick creation operator for the antimatter from phi star operator and annihilation operator for the particle from phi operator, that gives you the time ordering that I create antiparticle that goes to the position X and that gets annihilated. If I use opposite time ordering, I have to use phi first, then phi can be used as the creation operator of the antiparticle. Phi star is the annihilation operator of the antiparticle. So here, particle propagates from Y to X. Here, antiparticle propagates from X to Y. So that's why drawing the arrow actually makes sense for particles that have distinction between particles and antiparticles, because the arrow indicates either the particle is moving forward in time or antiparticles moving backwards in time. So as I emphasized, arrow is just a convention, but that has the meaning straight from this time ordering. One time ordering refers to particle propagating forward in time. Another time ordering is antiparticle propagating backwards in time. So that's the way the diagrams are drawn. So don't read too much into this idea of backward in time, but as a convention based on time ordering, that notation comes about naturally. Then, just by looking at the creation annihilation operators, you can algebraically work this out. And furthermore, I can combine this piece of one-time ordering into this contour integral. Because for the contour integral, where you have the pole slightly below the real axis, you can actually enclose this pole when the time is positive in the exponent. This exponential factor is exponentially suppressed along this half circle. You add to the integration contour. And time ordering is opposite. I need to enclose the pole slightly above the real axis by going through this semicircle. And by just adding them up, which is the original expression from this operator sandwiched between the vacuum state, summing them up gives you combination of this, the denominator E minus EP times E plus EP. That will give you E squared minus EP squared. EP squared is the P squared plus M squared. So as a result, I get E squared minus P squared minus M squared. That's nothing but this P for momentum squared minus M squared. So by summing these two pieces, I get manifestly Lorentz invariant expression. And the numerator, when you sum these two up, is 2E. That precisely cancels this 2E in the denominator so that I don't have any 2E factor downstairs. And this E integral for the contour integral combines together with this three-dimensional momentum integral in the modal expansion of the field, now into full four-dimensional momentum integral. So the integration volume is Lorentz invariant. Integrand is Lorentz invariant. And this is the form of the propagator we use, which is already a sum of sending particle from one place to another or antiparticle from the other place to another in the opposite direction. And this already contains a sum of the two. So that's why using propagator is a useful thing to do. You don't need to compute two different diagrams for two different time ordering separately, but using propagator, you can combine them together into a single diagram. And that's, of course, a lot easier. So computing two different time ordering separately is what people initially did in QFD. And these days, it is now called old-fashioned perturbation theory. But after Feynman invented this Feynman diagram, you don't need to do that anymore. You can compute the sum right away. So instead of two diagrams, you compute only just one diagram instead. And that's, of course, simpler. And that's what we do using Feynman diagrams today. Okay, any questions about this? Especially Miguel, does that answer your question? Good. Any further questions? Okay, so this is a fully Lorentz invariant expression. So let us clear up this electron-photon scattering once again. And as I said already, in a homework problem, you are supposed to show first that in the limit proton is at rest. Only zero, gamma zero, gives you non-zero amplitude. So 1, 2, 3 pieces are zero, so you don't need to compute them in the end. And once nu is zero, then because of this the metric of Minkowski space, this diagonal matrix, mu also have to be zero. So you're only supposed to compute this gamma naught matrix. And again, not gamma 1, gamma 2, and gamma 3. So simple 4 by 4 matrix multiplication is all you need to do for every helicity combination. So you compute this 4 by 4 matrix computation for helicity plus to plus, plus to minus, minus to plus, minus to minus. And that's fairly simple. And as I said already, you can interpret the result of that algebra considering angular momentum conservation for the case of the backward scattering, and also for the forward scattering too, if you like. And you can also consider helicity conservation in the massless limit, where Dirac fermion splits into two biofermions with fixed helicities. So these are the two limits that would intuitively make sense once you are done with the algebra. So I hope you would observe that once you actually do this homework problem. So that's the idea of the electron-proton scattering. We also learned that the sum of these two diagrams giving you a single propagator is the origin of the Coulomb interaction. So the Coulomb interaction is actually due to the exchange of the virtual photon. So that's another thing we learned from this example. And the photon propagator calculation just follows exactly the way I described for the Klein-Gordon field. The only difference is that now it got these indices, mu and nu, that would give you this minus g mu nu factor in the numerator. And that's all you need to know beyond what you have seen in the explicit calculation for the Klein-Gordon field. Okay, so that's it. So that completes the discussion of this electron-proton scattering. So any questions about this? Everything okay? All righty. So this actually leads to more general ideas on the Feynman rules. So here we looked at a specific example of electron-proton scattering, but this generalizes to what we call the Feynman rules, namely that if you have an initial state electron, and then you associate it with this positive energy solution to the Dirac equation for a specified helicity for the electron. When you have a final state electron, you associate it also with this positive energy solution for the electron with a specified helicity, but this comes with this bar. Again, bar means you take the Hermitian conjugate, so four-dimensional, the column vector spinner will turn into row vector with complex conjugate, and then you multiply gamma naught matrix on top of it. That's the definition of U bar. So this is sort of like initial state wave function and final state wave function, if you like, if you take analogy to the standard quantum mechanics. So immediately, when you see a Feynman diagram, you know what to put in for this, the initial state electron and final state electron. If you talk about antiparticle, then it's slightly different. For the positive energy solution, you don't actually annihilate the antiparticle. So in order to annihilate an antiparticle, you have to use the negative energy solution. But annihilation operator for the negative energy solution is not part of a psi field, but it's part of the psi bar field. So what you're supposed to use here is actually negative energy solution barred. So initial state positron comes with this V bar instead of V. That's why this notation of, using backward arrow in time actually is convenient. So positron looks like it's an electron going backwards in time for the negative energy solution. That's why you sort of end up with this initial state positron as if it were the final state. So you use this wave function with bar on it. So that's the meaning of this backward arrow. And of course, this is actually positron moving forward in time. But as far as the matrix element is concerned, it really does look like you end up with initial state electron, you end up with negative energy electron as the final state because this is barred. And so it looks as if antiparticle is indeed particle moving backward in time. But of course, interpretation is that this is really antiparticle moving forward in time. But at the level of writing down this Feynman rules, it sort of looks like this is backward in time. So that's why using this arrow notation is very convenient. So you draw arrows going backwards in time. So this final state positron now looks like initial state negative energy electron. So you also associate the solution B itself. For the initial state antiparticle, you pretend it is the final state negative energy electron. So you associate negative energy solution barred on top of it. And that's the Feynman rules. So that's why drawing arrows backwards in time kind of makes sense for the purpose of writing down the matrix element right away from the diagram. And that's why this is a convenient language. Again, that is not supposed to be read too much into it because nothing goes backwards in time. But indeed, amplitude looks as if this is the negative energy electron going backwards in time. So that's why we draw arrows backwards. And this is the way we can remember these rules very easily. So that's the whole idea of drawing these backward arrows. And we also talk about propagators for the photon, and we associate this factor as we talked about already. And in some cases, you also need propagators for the electron and positron and glue them together. So we will talk about that in a moment. But in addition to these initial state, final state, and propagator, we have this vertex we talked about. And vertex, as we said, is minus IE gamma mu in the unit where I take C and H bar to be 1. So this is all you need to know at the end of the day. This whole discussion about time-dependent perturbation theory, exponentiating a time order product, all that stuff, just reduces to this simple set of rules. What solutions you associate to the initial and final states, either for particle and antiparticle, and how you glue them together into diagrams by using these vertices, how each internal line is given by the propagators. That's all you need to know. Then you can write down this Feynman amplitude of the electron-proton scattering without even going back to any of these processes. You don't need to even remember creation-annihilation operator. You don't need to remember how time-dependent perturbation theory works. You just need to know these rules, and there you go. You get the Feynman amplitude. So that's the idea. And on the next slide, I believe I tell you what the propagator is for the fermion line too. And with that single addition to the rules you see on this slide, that's all you need to know to compute any processes you like in principle. It's tedious in many cases, I have to warn you, but it's straightforward. At the end of the day, you just multiply these 4x4 matrices, and that's all you need to know to get quantum mechanical amplitude of any of these scattering processes in quantum electrodynamic. So QED is a theory, and in QED, this is a rule, and with this rule, you can compute any processes you like in principle. Any questions about that? So this is the moment you can pat yourself on the back that you have achieved something very important. Now you know what QED is. Now you know what Feynman diagrams are. And in principle, you can go ahead and do any computations you like yourself. Okay, no questions? All right, so the single piece missing on the slide is this propagator for the fermion, and that's something we need to know. Also, another rule I forgot to mention is that how to associate initial and final state photon wave functions. That's given by this polarization vector we talked about, right? So when you expand the photon field, then that comes with the annihilation operator multiplied by e to the minus IPX, but also together with this polarization vector, epsilon mu, for different velocities. So when you annihilate a photon, that comes with the polarization vector. When you create a photon, that comes with the polarization vectors complex conjugated. Excuse me, something is ringing. So I'll be right back. Bam. So the idea is that when you have initial state photon, you associate this polarization vector, again, as if this was the wave function of photon or something. And for the final state photon, you associate this complex conjugated polarization vector, again, as if this were the wave function of the photon. And then you stick that in together with these vertices. So that's the way you can compute things. And for the propagator for the fermion, you associate with this funny object, I over P slash minus M. And this is again a notation Feynman invented. P slash is meant to be gamma mu with mu upstairs contracted with a P mu downstairs. So this is Lorentz invariant contraction because index upstairs and index downstairs. And instead of keep writing gamma mu P mu, he invented the notation P slash. So this is a shorthand notation. And you may be wondering, what the heck does it mean to have a matrix downstairs? Well, you multiply P slash plus M for the denominator and numerator. And if you do that, then downstairs, I have P slash minus M times P slash plus M. So that becomes P slash squared minus M squared. But it turns out that gamma mu satisfy this anti-commutation relation. Using that, I can simplify gamma mu as G mu nu in the end. So P slash squared as a matrix turns into just P squared as a number. So then I'm not talking about inverse of a matrix. I don't need to talk about that funny thing, but instead I have a matrix upstairs, which doesn't make sense. So this shorthand notation is meant to be this object. I gamma mu p mu plus m upstairs, and p squared minus m squared plus I epsilon downstairs. And this p squared minus m epsilon plus I epsilon is exactly the same thing you had for the propagator of massive Klein-Gordon field. The only difference is that I have something else in the numerator, which is this gamma mu p mu plus m. So that's the only difference. And so whenever you have this internal fermion line, I associate this propagator for the fermion defined this way. And again, I don't need to think anything. I can just write down the matrix element right away once I know what the diagram I'm looking at. So this is the complete set of Feynman rules. So whenever you compute any process in QED, every initial state particle is associated with their own wave functions of some sort. For electron, I associate that with a positive energy solution. For a positron, I associate it with the negative energy solution barred, because time flows backwards, quote unquote. And for the photon, I associate it with the polarization vector. And similar thing for the final state. In every vertex, I put in this factor of e to the minus IE gamma. And for every internal lines, I put these propagators for photon propagator and electron propagator. And that's all. So that's the way you can write down Feynman amplitudes, namely matrix elements in time-dependent perturbation theory, without ever going back to fields, creation annihilation operators, time-dependent perturbation theory, time ordering, all this business you can now forget. The only thing you need to remember are these rules at the end of the day. Okay, any questions about that, about this propagator for the electron and initial and final states for the photon? Everything okay? Good. Then we can start thinking about other examples of scattering processes. For example, this is a process. Oh, there's a question in the chat. For fermion propagator, we're ending up the virtual particle and antiparticle again. Yes, that's correct. Yes. So you add up two processes, again, because of time ordering, where the electron goes forward in time or positron going backward in time. So you sum those contributions up, and that's how you end up with this expression for the I over P slash minus M. So thank you, Chirag, for that question. Does it answer your question? I guess it does. Yes, thanks. Okay, good. All right, so now we talk about this new process. Electron and positron comes in as initial state. They annihilate and then produce a pair of mu1 and anti-mu1, where mu1 is also yet another Dirac fermion. So how do we write the Feynman diagram for this process? So here, electron and positron need to annihilate. So you bring them together and use the vertex to create a photon here. And then you use another vertex to put mu1 and anti-mu1 together. And this is a diagram. So you can come up with the Feynman diagram using these rules pretty much right away. And once you have a diagram, you can translate this immediately to the Feynman amplitude using these rules. So for the initial state electron, I associate that with a positive energy solution. For the initial state positron, I associate that with the bar of the negative energy solution. For this vertex, I have minus IE gamma mu. For this propagator, I have minus IG mu over Q squared. And for the final state mu1, I have U bar. Final state anti-mu1, I have V, again together with the vertex. So you can write down this amplitude right away. So this is exactly what I said. I associated this positive energy solution for the initial state electron with momentum P minus. Here's the vertex, minus IE gamma mu, and I forgot E in here. And here's the positron initial state, which is treated as the negative energy solution of the electron going backwards in time. So V bar for the full momentum P plus, and this photon propagator. And final state anti-mu1 is treated as the negative energy solution going backwards in time. So V of capital P plus. So this anti-mu1 has full momentum P plus. And here's a vertex minus IE gamma nu. And final state mu1 is positive energy solution barred with the momentum P minus. Again, this is it. So this process we have never seen in non-relativistic quantum mechanics, where matter and antimatter can annihilate, or matter and antimatter are created, can be computed again by the single line expression of the Feynman amplitude. And you can again go ahead and compute this, take square, and then compute the cross-section of this process. So that's how QFD works. So once again, all you need to know is to remember these rules. Once you know these rules, you can draw this Feynman diagram pretty much right away for the initial state and final state you want. And then you can write the Feynman amplitude right away for a given Feynman diagram. So everything is now transparent and straightforward. So that's the idea of the Feynman rules and Feynman diagrams in QED. Okay, any questions about this example?
Yeah, I had a question about this diagram. So in this diagram, like mass is not conserved, right? Because you have like two times the muon mass at the end, and that's like, I guess, like 200 times greater than the initial mass.
That's right.
So would this also be the case, like, where this process can only happen inside like some in some like Coulomb potential? And
actually, no, this process can happen. So what do you need to do? Send in electron and positron with a relativistic energy of at least muon mass c squared. And both of them come with the same energy that is bigger than muon mass c squared with a big momentum coming in. But if they are head-on annihilation, then momentum of electron and momentum positron cancel in a center momentum frame. All you need to add up are their energies. So total energy is now 2m mu c squared, and total momentum is 0 in that frame. Then the two muons come out nearly at rest, each of them carrying energy m mu c squared, but with very little momentum. And momentum is also opposite anyway, so they cancel. So that's the way you can fully conserve energy and momentum between initial state of electron positron and the final state of muon and anti-muon. So this process does happen, and I show the experimental evidence of that in a couple of slides. Thank you for asking that question. I saw another question. Cameron?
Yeah, I had a question. It wasn't pertaining to this example though, but I know like shortly after this, they kind of discovered mesons, I think. And so I was wondering like how to, like, can you apply Feynman rules to like meson theory, or does it kind of change?
So meson is a complex Klein-Gordon field. If you want to compute, for example, production of what is called the positively charged pion and negatively charged pion, again, they can be produced in pairs from this virtual photon exchange. Then what you have to do is replace this Dirac field with a complex Klein-Gordon field. And once again, you replace the derivatives in the Klein-Gordon Lagrangian by covariant derivatives, and then off you go. Then you can derive Feynman rules out of the Lagrangian in the way we did for the Dirac field. And then you use those Feynman rules to compute this diagram. So that is the way you compute the production of spin zero mesons.
Okay, great. Thank you.
Okay. I think Asha wanted to ask a question too.
Yeah. I understand that we have a strategy, given a Feynman diagram, how to write down the corresponding amplitude for that transition. But how do we know which Feynman diagram to write when given an initial and a final state? Are there like a number if we go to higher orders?
Yeah, so if you go to higher orders, indeed, there are infinite number of diagrams, but at a given order in perturbation theory, it's always finite. If you go to higher orders, for example, I can stop this virtual photon here and create the virtual pair of electron positron in between, which annihilates back to the virtual photon. So then this is called the vacuum polarization diagram. You have basically photon line, wavy line. You have a bubble of the circle of the fermion solid line and another wavy line. So that diagram also exists. You can also exchange a virtual photon here, which is called the vertex correction diagram. And also here, that's another vertex correction diagram. So it turns out that and there's another diagram which looks like a box I mentioned earlier. So there are 4 diagrams you need to compute now. So it's more complicated than the lowest order diagrams, but nonetheless, it's still finite. And if you actually stare at these diagrams and get used to it, you can pretty much immediately start drawing all possible diagrams without much thinking. And of course, if you want to have something more systematic, there are actually computer programs that generates all the Feynman diagrams for any quantum field theory at any different order in perturbation theory, so you don't miss anything if you actually rely on that kind of automated programs. And can we have Feynman diagrams with real photons using the max field Lagrange? Yes, we will look at some example of that in a moment too, like Compton scattering. So there are Feynman diagrams with the real photons in initial and final state, which you need for the Compton scattering. And we start drawing Feynman diagram for that too. Okay, does that answer questions from Usher?
Yep, thanks.
Okay, good. Any other questions here? By the way, I am planning on, I haven't really decided, but make this actually a part of the final exam. So this is also just single diagram, and you can compute this with the various heuristic combinations, and you can make sense out of them using the heuristic conservation and the angular momentum conservation. I will talk about that in a moment, so you should pay attention to that. But anyway, here's the experimental evidence. So this is a collider experiment where you accelerate electron and positron up to very high energies, and you let them do a head-on collision. Then electron and positron would disappear from the universe. And then this process creates a virtual photon at rest. Again, that doesn't conserve energy momentum because photon has energy but no momentum. So it doesn't satisfy the usual relationship between energy and momentum of the photon. But in terms of the intermediate state, that does happen. And this virtual photon now materializes into a pair of muon and anti-muon. And so this picture shows a series of detectors used in this experiment. And inside, what you are seeing is what is called a tracking detector. So the electron, in this case muon, ionizes gas inside this detector. So that leaves trail of electrons actually on the trajectory because of ionization. So they basically knock out electrons out of the atoms in the gas. And those trail of electrons get detected by shifting it by electric field to the end of the detector called time projection chamber. It's a beautiful idea invented by Dave Nygren, who was at the Lawrence Berkeley lab back in, I think, 70s or so. So this time projection chamber is a very useful technology to actually detect these charged particles traveling through a space. You know where exactly they went by looking at that. And then you see this another layer of detector called the electromagnetic calorimeter, where electrons and photons would shower and stop, but muons don't. Muon is what is called the minimum ionizing particle, so it doesn't create a bunch of showers and stop. Instead of they punch through it, they also punch through another layer of detector called the hadronic calorimeter, where particles that undergo strong interaction, like protons, and neutrons, and pions I mentioned a minute ago, would cause shower and stop. But muons don't have strong interaction either, so keep punching through and then get detected by this outermost layer of the detector. So when you see a hit in here, that's a muon. You know it pretty much right away. And you see one hit in a muon chamber, that's the name of the detector over here, another muon on the other end of this outermost layer, muon chamber. So you know this is two muons. And it's hard to tell in this picture, but there's a magnetic field applied to on this detector. So this track of muon is slightly bent. And one track is bent like this, another track is bent like that. So you know their charges are opposite from each other. If you really look at the real data in here. So you know that one of them is positively charged, the other one is negatively charged. Hence, this is a pair production of mu plus and mu minus. So this is an experimental evidence that the process I described on a previous slide really does happen. And now you can compute the cross-section of this process happening. So if you do an experimentalist working on this experiment, you predict how many muons you're supposed to count at the end of the in your data set. And they agree with the data. And that's the idea of QED. So it's a very predictive theory. based on these simple rules of the Feynman diagrams, you can really compute a process like this one, make a predictions on how often these processes happen. And then once you make that computation, that would be compared to the data, and they agree with a good accuracy within the first order perturbation theory we are computing right now. So, so that's the beauty of the theory. It's a highly predictive theory. It's simple enough that you can do actual calculations, but you can really use that predictions compared against the data, and they do agree. It's a successful theory, successful physical theory of nature indeed. So that's the idea. Does that answer Miguel's question? Miguel?
Yeah.
Okay, good. Any other questions? Okay. And of course, electron-positron can annihilate and produce electron-positron pair too. So in this case, you have two processes in Feynman diagram. One of them is the annihilation process I mentioned earlier. E plus E minus annihilate into a virtual photon that materializes into E plus E minus. But there's yet another diagram, which is similar to electron-proton scattering I mentioned. Namely, the electron emits a virtual photon that gets absorbed by another electron, a positron in this case. So the photon can be exchanged along the time direction, that's the annihilation diagram, or spatial direction, that's a scattering diagram. And this process requires you sum them up. You have two diagrams, you sum them, and you take square only after you sum them. And that's the process of E plus E minus going to E plus E minus. It has a name called Bauer scattering for somebody's name who probably first calculated this process. But anyway, so that's the way you can make prediction on this process as well. And here you see the electron creating a shower and deposit a lot of energies and stop. You don't see any hits on the outermost layers of detectors. So that's a sign that this is a particle that causes electromagnetic shower. Photon would do that too, but photon doesn't have a charge, doesn't leave a track. So having a track here and showing this shower in electromagnetic calorimeter is by definition an electron. And again, you look at the curvature of the tracks of both particles, then one is electron, one is positron. So you know that you are looking at this process, which corresponds to the Feynman diagrams I mentioned earlier. And again, you can compute it, compare that experimental data, and make predictions, not only the rate, but also angular distribution of electron, for example, and they all agree. And that's a virtue of having a predictive theory of quantum electrodynamics. Okay, any questions about that? Good. And now we'd like to talk about a process where that involves real photon initial final state. And I think Shiraz was asking this question. So in this case, I can study the process where electron and positron annihilate, not into a single photon that doesn't conserve energy momentum, but into two photons that can conserve energy momentum. And this is a process that indeed happens. If you have electron and positron, they come together, annihilate into two photons. And this is a process, for example, the condensed matter people use in experiments trying to measure the distribution of electrons inside some material. You slowly sending a positron into the material. And positron meets an electron, it annihilates and produces two gamma rays, which is energetic enough that can escape the material and you can detect them from outside. And then you can measure the position of the gamma ray where it came from. And there must be an electron at the location. So that tells you how the electrons are distributed inside the material. So this positron annihilation is actually a useful tool for condensed matter experimentalists to measure experimentally how electrons are distributed inside the material. So these processes, again, do happen. But now that you know Feynman rules, you can start thinking about how to draw Feynman diagram for it. Okay, so I can follow the arrows as we did before. Electron goes to this positron, but through now an electron propagator in between, and then attach these photons to vertices. So that's one diagram. Again, that's very easy, right? So once you know these rules, you can immediately write down the Feynman amplitude for this. The only thing you need to be careful about, though, is two photons in the final state bosons, and they have to follow Bose statistics. So there is another diagram where two photons are interchanged. So in addition to this diagram, there is another diagram where two photons are interchanged, like this. But either way, you can write down Feynman amplitudes right away. So first, you follow the arrows for the electron. Initial state electron has this positive energy solution. And here's a vertex gamma nu. But here you create a photon, so you associate the complex conjugate of the polarization vector, epsilon nu for the photon 1. And this nu index is contracted between this gamma nu vertex and gamma nu for the epsilon nu for the polarization vector. Then I have this electron propagator in between in green, where this 4 momentum Q of the electron propagator is initial electron momentum P minus photon 4 momentum Q1. So P minus Q1 is this Q for the virtual electron. Then comes the second vertex. Here you have gamma mu, now contracted with the polarization vector for the second photon, epsilon mu nu star, and goes over to this the positron, which is represented by the negative energy solution as if it were final state. Again, this convention of antiparticle going backwards in time. So I use V bar solution to the Dirac equation, and that's it. And if you're worried about the structure here, U is the 4-component row spinner. Gamma nu is a 4x4 matrix. Propagator is a 4x4 matrix. Gamma mu is a 4x4 matrix. V bar is a 4-component row spinner. So it makes sense. If you multiply them together, it becomes a number. It's no longer a matrix. And all the Lorentz indices are also contracted between epsilon nu. You have the 4-component of the polarization vector, as we have discussed before, on top of this gamma nu matrix. So you find a linear combination of 4x4 matrices here, but it doesn't change the structure of the matrix multiplication. So that actually works out to give you a single complex number at the end of the day. And the other diagram where two photons are interchanged, then I need to stick in the polarization vector for the second photon first at this vertex. And 4 momentum of the virtual electron changes now, because now K is P minus minus Q2 instead of Q1. That's why I use a different symbol for the 4 momentum of the electron, for the electron propagator. Then comes the polarization vector for the first photon and goes over to the same wave function of the initial state positron. So once you have this process in your mind, all you have to do is to think about these two Feynman diagrams. I went too far, I'm sorry. So by looking at these initial state and final state particles, you can sort of see how you can glue them together into Feynman diagrams pretty much right away. And for this diagram, you already have a prediction that the Feynman amplitude looks like this. But then you need to remember there's yet another diagram to be consistent with the Bose-Einstein statistics of the photon, and that will give you yet another Feynman diagram and hence Feynman amplitude. Then you sum them up, and that's the total Feynman amplitude. And using this, you can again compute the annihilation cross-section of electron and positron. You can compute the angular distribution of the photons and so on and so forth from these two diagrams and from these matrix multiplications at the end of the day. Okay, does that answer your question, Chirag? Was it Chirag? Why does this interaction require virtual fermion exchange instead of virtual photon? That's because I can't draw a diagram where E plus E minus annihilate into virtual photon going to two virtual photons. There is no vertex. The photon will interact with two other photons because photon would couple to anything with electric charge, but photon itself doesn't have electric charge. So there's no 3-photon vertex in QED. If you go to a different theory, for example, you have a theory of something called W boson in weak interaction. W boson is also this wavy line, spin 1 particle, but it has an electric charge. So in that theory, you have a vertex of photon coupled to W plus and W minus. So you have a vertex of 3 wavy lines in that theory. But that's only because W boson has a charge, but photon doesn't. So that's why there's no triple photon vertex. Therefore, virtual photon doesn't lead to this initial state to that final state of 2 photons. And that's why we're not drawing it. Does that answer your question, Chirag? Okay, good. All right, I think time is up. So let me finish up here. And so what we would like to talk about next is once you have these Feynman amplitudes, of course, we'd like to compute the cross-section at the end of the day. And from this point, I will describe how that is done. And once you know also these rules in how to compute cross-sections, then you really have all the rules at your fingertips to compute any process you like in QED. So that's the idea how we'd like to close up the this semester of the QFD. Okay, any questions?
I just had a logistical question about the final exam.
Yep.
Are you still thinking about offering either like dead week or finals week? Or?
Oh, no. So I was told that actually the second option I mentioned was after the end of the semester. So it has to be done in the first week. So what it means is that a week from this Friday, I'm going to post the final exam problem, and it will be due a week later at the end of the first week of final week.
Okay.
Okay, I hope that works for everybody. Okay, any other questions? All right, so I see you on Friday, and that will be the last lecture of this semester.
Thank you.
Bye.
Thank you.